Okay, in this presentation we are going to look at information theory and in particular how to calculate entropy. So it's just a short example really. We have a discrete memory list source, a DMS, and it has four symbols x1, x2, x3 and x4, and each have the following probabilities: 0.4 for x1, 0.3 for x2, 0.2 for x3 and 0.1 for x4. So calculate the entropy, okay, h of x. Okay, that's calculate the entropy of x basically. And find the amounts of information contained in the following messages: x1, x2, x1, x3, and x4, x3, x3, x2. Okay, that is a sort of intentionally an awkward looking thing. Okay, so that's sort of, if you think that's a little bit annoying to look at, that's the point. Okay. Anyway, so here is our entropy formula here. Now, in this case, I have slight variations of the same formula here around the place. But here I have minus the summation of the probability of each term, of each symbol, okay, times log to the base 2 of that probability, okay. Just in this case, I'm using log to the base 2. I use log to the base 2 in most of my videos, but every so often I might use the natural log or log to the base 10. But anyway, log to the base 2 here, which means our answer will be in terms of bits. Okay, so what do we do? Essentially what we do here is we multiply the probabilities by the log to the base 2 of those probabilities. And essentially what we do here is for each term we precede it by a minus. So we're effectively subtracting lots of terms from each other, but they're actually negative numbers. So it's a double negative once you proceed, and that turns into a series of positive numbers down here. So minus 0.4 log to the base 2 of 0.4, minus 0.3 log to the base 2 of 0.3, minus 0.2 log to the base 2 of 0.2, minus 0.1 log to the base 2 of 0.1. When we work that all out, we should get 0.5288 plus 0.5210 plus 0.4644 plus 0.3322. So just to be clear, this is a minus times a negative number. Okay, so that turns into a positive. So that negative becomes a positive down here. So we have we're adding four positive numbers here when it looks like we're subtracting a bunch of numbers here. That just throws people when they're getting used to this for the first time. Anyway, when we add that all up, we get 1.85 bits. Okay. Now, so the first message. So essentially what we have to do here, this is actually fairly straightforward. So it's essentially what we have to do is recall that these are independent events. x1, x2, x1, x3, that they're all independent events from each other. So the probability of this message is the product of each of the probabilities. Okay. And so that works out to be 0.0096. That's 0.4 times 0.3 times 0.4 times 0.2. The information of that is simply minus log to the base 2 of that probability, that overall probability. So minus log to the base 2 of 0.0096, that works out to be 6.7. Okay. And same again for the message 2, x4, x3, x3, x2. That's 0.1 times 0.2 times 0.2 times 0.3. That works out to be 0.0012. And when we get minus log to the base 2 of that, we get 9.7. The bits per symbol there is how we express the information. Okay. Right, that's it.